Miky, I didn't know you did so much. Oh. After this very impressive talk and achievements, I'm going to tell you a very simple story. That's the title. I thought, in view of the mixed audience, I'll tell you something rather simple, but I'm sorry, nevertheless, a bit of science. I hope the time will allow me to describe two simple problems that were studied by huge simulations, not mine. I don't know how to simulate. I had students who did some simulations, but very simple ones. But I'll try to convince you that when you do a simulation, you should be very careful what you put in, because sometimes you put in what you want to get out or whatever, I don't know. And in many cases, you can do without the simulation or use the simulation to support your idea. But first of all, how do I move things here with this? Like this. I thought I will be the only one, but Uzi Even said he was not a student of Rafi. I was not a student of Rafi either. I was actually a student of Shalom Ber, the late Shalom Ber. And I knew Rafi since he came to the Hebrew University. When was it? 68, maybe. 68. Is the Volvo still going? Is it? It is still going?
François is there, yeah.
Still using it? François is still using it from 68?
Yeah.
That's like 50 years. That's very impressive. So, I was not Rafi's student, but I was his teaching assistant, together with my good friend Moshe Shapiro, the late Moshe Shapiro, who was Rafi's first student. I was actually, as someone mentioned, Moshe was doing a molecular rate processes. The red book, I remember it, very impressive. And that's not important. Anyway, I did my PhD with Shalom Ber, doing some rather formal statistical mechanics. I liked it. And one day, Maurice Cohen, who was here, he left because he has, I don't know, Talmud lesson or whatever. It was at Maurice Cohen, there was some party, maybe you remember Rafi. We were sitting and you were asking me, Avinoam, what are you planning to do next? It was towards the end of my PhD. I was very naive, I had no idea what I'm going to do next. These were times, you know, I didn't think about what I'm going to do next. So he said, come talk to me tomorrow. I came to talk to him. He asked me, would you like to join the Weizmann Institute? Well, sounds interesting. You remember? I remember. The next day I was interviewed by Schneur Lifson. I was offered a position at the Weizmann Institute. I think Rafi was supposed to come to the Weizmann too, but something happened. Never asked you why. But I can tell you that Schneur was very nice to me. But then 2 years later, after the postdoc with Ludwig Hoffacker and Karl Kompa, Rafi kind of convinced me to nevertheless join the Hebrew University. It was very easy because my wife strongly preferred Jerusalem. And then, you see, I wrote it. It's good, so I don't forget. In the short period, after seeing Lifson, but before going to Germany, we had a few months together. Rafi came with a paper. It was called Entropy 1 with Dick Bernstein. It was about entropy, and then there was a paper, a preprint, trying to define temperature. That's where we started, and this was the beginning of surprisal, I think. And anyway, I came back to the Hebrew University, and you see this potential energy surface. I never worked on potential energy surfaces, but I can tell you that this more or less describes my relations with Rafi since then. There were ups and downs and valleys and hills and so on. Now we are old and happy to go, as like in the song, but not Rafi, me. Anyway, so that's it. And I will tell you 2 examples. I may go over time a little bit, but we have plenty of time. The first one is about so-called amphiphilic aggregates. They are called Micelles. These are molecules. I promised Itamar he will understand everything. You can teach me something here. So these are molecules that have hydrophilic, they like water heads and tails. These are hydrocarbon chains. There can be 1, there can be 2. Depending on their geometry, they can form either spherical micelles or elongated ones, they can twist, or they can form biological membranes. These are phospholipids. Of course, the membrane is more complicated, but these are the 3 models. And in 1980, I suggested to my friend from UCLA, Bill Gelbart, let's work on these problems. And there are two scales of problems. One of them is statistical thermodynamics of their assembly, self-assembly. Now everybody is talking about self-assembly. At that time, very few talked about self-assembly. So these are self-assembling structures, and there are many questions about their phase behavior and the role of dimensionality. Another issue is about the microscopic structures of these aggregates. So in 1981, a pretty famous guy now, Ken Dill, he was a postdoc of Paul Flory. Paul Flory got the Nobel Prize for polymer physics, or polymer chemistry, I guess, or physics, or polymer physical chemistry, whatever. And they had a model for the chain packing. This, by the way, is from their paper, 300 citations, PNAS. And it was a very nice talk that he gave. It was a stochastic model, how these chains go and they go to the middle and so on. This is a terrible picture. It's wrong. It appears in all books. But you cannot pack chains this way. There is no room. You see here on the lattice model, you can see it a little bit. But they assumed in their nice model, they assumed that they couldn't do otherwise. Their chains could only go into the center. You see, they don't go back. And they predicted an experimental result. The experimental result was about the order of the chains. How do they order? Do they become more ordered or less ordered? And they predicted that they become more ordered as you go along the chain, as you go to the center. Experiment showed it's wrong. When I heard Ken Dill, I thought, well, it's a nice work, but I could do it otherwise. I could do it by entropy maximization, subject to constraints, or if you want, it's the same thing. It's minimizing the free energy. It's exactly the same. So we wrote a paper. It's a better paper. It's a correct paper. Much less cited, of course, but doesn't matter. We allowed the chains to go back. Now I'll show you in one slide how it goes. You write the free energy. The free energy, we want to know the conformations of the chains. You can use a model. It's called rotational isomeric state model. It doesn't matter. You see there are many chain conformations. Look at one. I'm doing it simply. I write the free energy for this chain. It has energy. Alpha is a conformation. P of alpha probability. E of alpha is the energy, the trans-Gauss energy. KT, you know, Boltzmann constant temperature. P log P. Some people call it Shannon entropy. No, it's Gibbs entropy. It's okay. It's Boltzmann entropy. It's entropy. And now what you have to do is minimize the free energy. That's like maximizing the entropy, subject to whatever constraints. These are physical constraints. The physical constraint is very simple. We require that the density of these segments here will be uniform, which is typical of liquids. That's it. That's all. So this is how the constraint is written. Next thing, you minimize the free energy. And the next thing, you get the probability distribution. This is called the partition function. Here's the exponent. Beta is 1 over KT, energy. And here You heard this term many times today. These are Lagrange multipliers, except here they represent lateral pressures. These are the pressure. And everything depends on geometry, and you can do that, and you can also calculate all kinds of thermodynamic properties, but we have no time for that. It's also possible to derive it differently. You look at the chain, take the chain out, and then you have a hole here. You calculate what is the probability of a hole. This is a partition function. If Itamar was here, he would recognize. He also calls it Z, but I'm older, so I came first. And then all you do is you take the logarithm, you expand it in powers, and you get exactly the same result. And then you compare to experiment. We did a lot of work here. Now I'm telling you, at that time, the late Klaus Schulten had a huge machine with many hundreds of processors, and they did a huge calculation. And they calculated what is called the bond order parameter. You go along the chain, you calculate the average of the second Legendre polynomial for different bonds. It is measured by deuterium NMR, so you have it. The dots are experiments. This is for the chain with a one double bond, so there's a dip. Forget about this one. And this is a mean field calculation, our calculation done by Debbie Fatal. There are no adjustable parameters. Udi Marcus was here in the meeting. He said he hates adjustable parameters. I also don't like them. No adjustable parameters. This is it. Klaus Schulten also, they did also calculation, got the same result, more or less. But no theory. Okay, so this is one example. The problem with simulations, of course, that you have to use potentials that you don't always trust. When you only have a simple constraint, you don't need to count on any assumptions. Okay, second example. This is a famous picture. This is a virus. It's called bacteriophage. It's very old. You see 1962. Meanwhile, there are thousands of them. And you see all this spaghetti around. It was all inside this little head here. This spaghetti is DNA. So how could all this spaghetti be inside this little head? It must be extremely condensed, huge. Now this DNA, you see DNA? It's nice. And it is very stiff. It is highly charged, everybody knows that. This is also stiff. It's highly charged. It's hard to bend. It's about 50 nanometers, what is called the persistent length. The persistent length is the length that it bends naturally by fluctuations, thermal fluctuations. So you see that's a persistent length. That's about the persistent length. It's bigger, or it's about the same like the head. So there is a lot of work needed to be done to put the DNA inside. The work is done by motor proteins. We don't go into that. They are very powerful, these motor proteins, and they can put all this DNA into the capsid, into this box here. And there are old and new measurements of how the DNA is organized. These are electron microscopy, very famous picture. They form a torus or a spool. So we decided to do a theory. This one I added in the break because we are ahead of time, so I thought I can tell you how viruses work, to those of you who don't know. These are bacterial viruses. They infect bacteria. Animal viruses work a little differently, but the structure is the same. There is this box, there is a tail, and you see they look like spaceships. They come, they anchor to the membrane, they inject the DNA. The DNA is pulled by proteins and whatnot. It is incorporated into the bacterial DNA, and it is replicated, and it kills the cell, and so on. So that's how viruses work. Very similar in animal viruses, except that they go inside. Anyway, so we wanted to do a theory. We did a theory. By the way, these are DNA toruses. This is a cut We know exactly the strand-to-strand distance is 28 angstrom. This is, by the way, another entropy, very interesting. This DNA in solution, it's called, it's a random coil for system length. It is surrounded, because it's highly charged, it is surrounded by counter ions. Say positive counter ion, not say, there are positive, I meant monovalent cations. If you add polyvalent cations, what they do, they replace the monovalent ones. If you want, they serve like glue. The DNA is forming a ptosis, like here, and the little ones go into solution. That's the driving force. The electrostatic energy is the same, but what is changing is the entropy. When this little guy goes, here they are bound, but here they are in solution. So it's a gain in entropy. That's what drives the transition. Anyway, Partition and Rao and Partition measured different, not here. They measured the forces that act between the DNA strands. You cannot push them too much. We know that whether there are polyvalent or monovalent cations, there is a very strong repulsion starting at around 28 angstrom. The distance here is 28 angstrom, here too. Okay, so 2.8 nanometers. With my student Shelley, she's now a professor in the Technion, we did a simple theory, and Bill Gelbart and his postdoc, James Kint. Very simple theory, DNA in, DNA out. You write the free energy. There are more complicated equations, but everything is here. The free energy of the system is the free energy of the DNA in and the DNA out. And this is a function of how much is in, how much is out. And whether inside or out, we have two contributions to the free energy. One is the repulsion, and this was measured by Partition. We have the result, we know it. He measured pressure. We integrated the pressure. We got energy, or free energy if you want, potential of mean force to be exact. And we also know the bending energy. The bending energy goes like 1 over r squared, psi kt or whatever. So we know the bending. It's hard to bend. So obviously a lot of work must be invested by the motor protein. It does it. Single molecule measurements by Bustamante, mainly in Berkeley, and his student, now professor himself. They measured with single molecule experiments. They can measure the force that the motor has to exert in order to load, and it goes like this. That the force is going to about 50 piconewtons, 30 piconewtons. And this is as a function of how much you load into the virus. It's like you're winding your old watch, right? With a spring. You pay more and more energy. That's where it stops. We calculated it. We calculated the different contributions. It goes like this, you see that. And I want to, if you can read, Smith, who did the original measurement, mentioned that their better measurements are in better agreement with our prediction, which is nice. It's no big deal, because our free energy only took two pieces from experiment, the repulsion and the bending. We cannot go wrong. They can go wrong. We cannot go wrong. Okay. And then we also predicted, Bill Gelbart came to me once with a question that he heard from someone, can we perhaps stop the ejection by osmotic pressure outside? I said, I don't believe, but let's do the calculation. We did the calculation. One adds a PV term, that's like osmotic pressure. Experimentally, you can increase osmotic pressure in solution. You add PEG, that's a polymer. Turns out that the free energy above a certain concentration of this PEG develops a minimum. This is the free energy as you release the DNA out. It goes out. The free energy goes out as DNA is ejected. but then there is a minimum. If there is a minimum, you can be stuck here. So the prediction is that if you have 3 atmospheres or more, maybe you can stop the ejection. So what's the prediction? This is an experiment. You stop the prediction. You stop the ejection. And this is when my friend Bill Gelbart became an experimentalist. He's not doing theory since, only experiments. But now I will finish. How am I doing with the time? Oh, 2 minutes. Please give me 2, like, you know, in soccer, they give a few. And
2 plus 1. Okay.
No, Miky, you're the expert on sports. Listen, I waited many years. You can wait 3 minutes. But this is important. People did simulations too of the same thing. There is a guy, he's a big simulator, Steve Harvey, and he did some beautiful simulations. I saved you some. And he concluded in his calculation that 80%, 88 or 70, depending on the virus, are entropic. How is he doing the entropy? He's calculating the force of loading. You integrate the force, you get the energy. If you have the energy, I'm sorry, if you know the work, then you know the free energy. Also, he has in his model, which I'll show you in a second, in 20 seconds, he knows the energy. He subtracts the energy from the free energy, gets the entropy. He finds that most of it is entropy. I got his paper to review 15 years ago, but I was busy with other things at that time. I said, no, thanks. But then at some point I decided, this was like 2 years ago, I want to understand where this entropy comes from, especially because he said that what we did is wrong, because we don't have entropy. Okay, this challenged me. Now I tell you where the entropy comes. He couldn't explain where the entropy comes, but I'll tell you where the entropy comes from. This is a free chain. This is his model of the DNA. You know, you model, you do a simulation, you make a model. DNA is not a chain of beads, but okay. So you have a chain of beads. You say in solution, you calculate the persistent length, then there is some assumption about the interaction between beads, and that's it. Now, as I told you, he's loading, calculating the work, subtracting the energy, get entropy, 88%. So I came with an explanation. I tried to connect with him. I calculated it. What happens is when you put this chain and you put it into the capsid, it cannot really move. So all this freedom, most of it is lost. So if here, to get the persistent length outside, it has about 16 degrees freedom. When you put it inside, it's about 3 degrees. I make the simple calculation. Delta S is nk log the omega, the probability. What you have in the confined, in the free, you calculate, you get the entropy. The entropy is the entropy of confinement. That's what in his model. But here is the important lesson. The entropy that he calculates depends on what he assumes on the diameter of his beads. If you have smaller beads, the entropy loss will be smaller. Practically, what he was doing, he was using hard beads. This is a better calculation, but we don't need it. Here is a difference. I'm finishing. There are 2 slides. 2 slides, and thanks to Rafi. Look, we assume that we have hexagonal packing, and we got from experiment this interaction. We assume perfect. So if you want, it's a harmonic solid. It's a bundle. What they have are hard spheres. Hard spheres. Take a cut, and you get hard disks. Hard disks are known. They do not have energy. They have entropy. That's the entropy of motion of this. That's the origin of his entropy. I tried to explain it to him. He was not convinced for a while. But then he said, Avi, Thank you. Now I understand. And that's the difference. Basically, we used a rather soft potential, and they used a very stiff potential. So you have to know what you put into your simulation. And I'm on this happy note, Rafi. Thank you very much for. Did I say that if it was not for Rafi, I wouldn't be standing here probably, because I don't know if I would get an academic position. But thank you, Rafi. And, I preferred another one. I didn't know which one is better. This one is in English. Okay, that's it. Thank you.